Okay, so we are going to move forward today with your old friend, the ideal gas law. We're going to talk about some of the laws that got up to there, but we're going to end with that. Let's keep going. The first thing we got to talk about is pressure. Pressure is something we can measure. Maybe you remember the formula, but pressure is equal to force divided by area. Let's talk about force. Force is measured in what? It's measured in newtons. Area is going to be measured in meters squared. So this guy right here is pressure, and that's going to be measured in newtons per meter squared. Now, that does have a fancy unit, and that is a Pascal. All right, it's a two-letter unit named after a guy, which is why it's a capital P. Nice. Now, something you should keep in mind, if you have a Newton and you spread it over a whole square meter here, remember a Newton is like half a pound, and you spread it over an entire square meter, a Pascal is really small. So typically, I mean, Pascals are a thing, but it's going to be more common to talk about kilopascals or megapascals, usually kilopascals. So each one of these is 1,000 pascals. All right. So important numbers you should know. You should know what the atmosphere is at. The atmosphere is about a 101.3 kilopascals. All right. So if you wanted to convert it to pascals, you kick the decimal back 3. So it's 101,000 pascals for pressure. Now, this is what pressure is, but let's talk about like why it's done this way. All right, we're going to be talking about gases a lot today, so we want to talk to you a little bit about like why gases have pressure at all. So if we have a gas and we put it in a container here, remember gases are made up of tiny particles, right? You know, atoms or molecules, depending on which one it is. Now, all of these pieces here have some kinetic energy. That means they're moving very fast. They're very small, but they're moving very fast. We know they've got kinetic energy because they've got some temperature, like before. Now, occasionally, these guys will slam into the wall, all right? Now, when you have a particle that slams into the wall, it's going to not go through the wall. It's going to bounce off the wall in one way or another at some speed. Now, that means that it is applying a force to the container because the container is applying a force to the gas particle. Now, this force right here is going to be over the entire area. And that is what you get for pressure. So pressure is formed by the particles slamming into the side of the container and bouncing off of it the other way. All right, so that's why gas is under pressure. It's the same thing for a liquid too, because the particles are moving around like that. Okay, so let's talk about some old friends here. Our first old friend is Boyle's law. Boyle's law compares two things. Do you remember what it is? Boyle's law compares volume and pressure, with everything else staying the same. Right? That's going to be a situation for all of these. So we'll put a note here just because it's the first one. So we're going to have a constant temperature. Okay, and everything else. But now, if we change the volume of a gas, what's going to happen to the pressure? If I take this box here, this box has a bunch of gas in it, and if I make the box really, really big, I'm not changing the amount of gas in there. Now, are they going to run into the wall more or less? They're going to run into the wall less because there's more space in there. The wall is a smaller fraction of the area there. So What does that mean? That means that volume is not proportional to pressure, but volume is inversely proportional. So if we graph these guys, if we put pressure here and volume here, Boyle's law says that you're going to get something like this. So it's a hyperbola, it's an asymptote. Sound good? Alrighty then. Let's do your other old friend, Charles's law. Okay, Charles' law compares two things as well. Do you remember which two? Charles' law compares temperature and volume. Okay, so let's talk about what happens here. Now, for this one, pressure is going to stay the same. Okay, so pressure is not going to increase for him. So this time, I've got a box. It's got gas in there. It's got 9 gas molecules in there, we'll say. And I'm going to heat it up. So it's going to become hot. We'll make it, I already used red. Oh, well. So what's going to happen to my grouping here? Well, since the pressure has to stay the same, the volume is going to increase. So they're not going to hit, now because the temperature goes up, the kinetic energy is going to go up, right? So they're moving faster, but they're not going to hit the wall at any higher rate. So that means they're going to hit the wall less, but harder, so it averages all together here. So that means temperature is going to be proportional to volume. As temperature goes up, volume is going to go up, as long as pressure is constant. Okay, if we put it in a graph, we'd have our temperature here, we'd have our volume here, and then we'd have it go up like that. Okay, sound good? Situation where this comes into place in the real world would be like a hot air balloon. Hot air balloons don't have any pressure on them because they are open, but you heat it up and they expand. All right, let's do another one. This is the less famous of the group here. The Gay-Lussac's law. Maybe you remember it, maybe you don't, but we've kind of already hit it. Gay-Lussac's law compares temperature and pressure. All right, the difference is though, for this one, volume is constant. Okay, so for here, we've got a container and we've got another container here. So this is the cold one. We'll have the red one be the hot one. So we're going to light this one up. Now our gas molecules, we'll start off with the 9, are going to be moving faster here, right? They're going to be moving faster, but they don't have more room, so they're going to be hitting the walls harder. So as temperature goes up, pressure is also going to go up. So that means they are going to be proportional. We'll put it on a graph and put temperature here and pressure there. It's going to make a straight line. Ta-da! All right, there's one more, kind of the weirdo of the group here. It's Avogadro's law. I know you know the name, but you might not remember this particular law. Okay, this one compares the moles of gas, all right, to the volume. Now this keeps the temperature and pressure constant. Well, what do you think is going to happen if these guys stay the same? I have a container and I increase the amount of gas in here. So I'm going to go from 4 gas particles to 10 gas particles, or well, let's go with 8. Well, what's going to happen is the volume is going to go up. 1, 2, 3, 4, 5, 6. Because they need more room, because they can't change their speed because the temperature stays the same. They can't change how hard they're hitting stuff, so the pressure is going to stay the same. So the moles of the gas is going to be proportional to the volume. If we graph this, moles, remember moles is N because M was taken, and volumes over here, it's just going to make a straight line like that. The more gas you have in an area, the more volume you're going to need for that, unless you increase the pressure or whatever. Nice. Now these all combine together, all right? So what we can do now is, since we know that some stuff remains constant and proportional, right? So I know that pressure is going to be proportional. So let's say proportional to temperature, right? Temperature goes up, pressure goes up. But I also know that temperature is proportional to volume. So I know volume is going to go there. And I also know that the moles is going to show up here, right? So I know that these guys are all proportional in this way. If moles goes up, pressure has to go up, or volume has to go up, or temperature goes down. So it's like this. Now, this means whenever you have a proportionality, all you got to do is throw in an extra guy, and we can make it into an equal sign. All right? So I'm going to move the NT over. So I'm going to have VP over NT, and this is going to equal K. K is just some constant, all right? It's nothing special. It's just some random value here. So it's just some constant. Now, because VP over NT is going to equal some constant, what I can do is I can have two situations linked together. I can have V1 P1 over N1 T1 equals K, which is just that constant. Doesn't matter which values I picked, it's just going to equal something. Now, if I tweak it a little bit, I could have a different volume, which would mean I could have a different P or a different N or a different T. I could have all of these be different. And what we're going to do is we just cut out this middleman here, and we get these two guys equal to each other. All right, this is the combined gas law. The combined gas law just merges those previous four laws into one equation here. So we've got V1, P1, N1, and T1. Okay? All of these can have any units to them. For pressure, you could use atmosphere, or you could use Pascal, or you could use kilopascal. It doesn't matter, but this guy, its neighbor, has to be the same. Likewise, for volume, you could use liters or you could use meters cubed, but it has to be equal over here. N is always going to be in moles, but I suppose you could use particles if you really wanted. Now, temperature is an exception. Temperature must be in Kelvin only, because you're using an absolute temperature here. So you can't use 2 Celsius temperatures. I'll give you a really easy example if you don't know why, because what if it's at 0 degrees Celsius? Well, you just gone and blown up math by putting a 0 in a denominator. So that's why you have to use Kelvin. Now that doesn't happen in Kelvin because you can't have 0 Kelvin, which is coming up later in the week. Don't worry. So that's your combined gas law. Now what scientists were thinking is, well, this is all well and good, but why do we have to have 2 different states to compare? Why can't we just figure out one state in a standard setting? Okay, so we'll call this one our standard, and then we'll compare it to the new one all the time. You know what? That's exactly what they did. So they found the value of the K, all right? And that takes us to your friend, the ideal gas law. So the ideal gas law has the same situation here. I'm gonna approach it from what we just have. I know you probably know it already. So we've got P and V on top, N and T on the bottom. That's going to equal a K. What they did is they figured out the value of this K, all right? And they replaced it because it wasn't just any constant now. It was the ideal gas constant. So P over NT is going to equal a capital R, okay? Now, they figured out the value for this. It's got a couple different ones depending on your units, but the value you're going to use in physics is going to be 8.31, and this is going to be, we'll write it out the long way first, in pascals meter cubed divided by mole Kelvin. All right, so that's that. Those are the units because it's just straight from here. So when you're using 8.31, you have to use pascals and meters cubed. Now, in reality, it's going to look different on your formula sheet. The reason why is because they break it down just a little bit. A pascal, remember, is a Newton per meter squared, and this guy is a meter 3. So they cancel out those, and so you get a Newton meter, which means that this is going to turn into 8.31 joules, because a Newton times a meter is a joule. Not that kind, sorry. All right, moles Kelvin. Awesome. Now, maybe you're familiar, maybe you remember, you have 0.0821, I believe, and that is going to be atmosphere liter over mole Kelvin. That's from your chemistry days. And we wanted to write that down just so you have a point of relation. Right? They are very similar to each other, these two values, but we're going to use the 8.31, the one that's bigger, because that's the physics units. Now, they usually don't write your ideal gas law like this. They usually write it in your old friend, PV equals nRT. Nice. So R is this value here. R has a name. It's the ideal gas constant. It shows up in lots of other places that are related to gases like this. Ideal gas constant. And then T, just like before, must be Kelvin. N is going to be in moles. V has to be in meters cubed. And P must be in pascals. So when you're using the ideal gas constant, it locks you in for units. You have to use the units that are matching your ideal gas constant. If you type in ideal gas constant to the internet, you'll find 100 different combinations of units with it. My recommendation is you just stick with one of them. Since we're doing physics, we're going to use this one, and then you just convert everything to pascals, meters cubed, and that stuff. That's what I would do if I were you. Let's do a practice one. Okay, so for this one we have an ideal gas at room temperature, temperature of 22 Celsius, trapped in a metal cylinder, a volume there, and pressure that. Calculate the number of moles. Easy money. So we're going to have PV is equal to nRT, your old friend. Pressure is 1.6 times 10 to the 6. All right, I know it's hard to see there. Just take my word for it. Times V, volume is 0.2. It's in meters cubed. Awesome. Times N. N is what we're looking for here. So there, R is 8.31, always will be. T, it's not 22, remember. You got to switch it. So it's going to be 295 because it's got to be in Kelvin. If it ain't Kelvin, it ain't right. So what we're going to do here is solve for N. It's math time. You're going to get 130.5 moles. Wonderful. Easy. The gas has a molar mass of that. Calculate the density of the gas in the cylinder. Awesome. Hey, so what we're going to do now, first we're going to figure out the kilograms. So we know the moles, and even if you don't know what molar mass means, just look at the units here. It's kilogram per mole, right? So if I've got 130.5 moles, what I can do here is if I multiply by 4.3 times 10 to the minus 2, over, that is in kilograms per mole. So what's going to happen with this now is the moles are going to cancel out, and that leaves me with kilograms. So if I do this, the amount of kilograms that I'm going to be left with is 5.6 kilograms. Is that our answer? Not quite, but it is close because it wants the density. So how do you figure out density? Remember, density is mass divided by volume from the good old days. So we know our mass, we know our volume. Our volume is the same as it was a second ago. So 2. So we're going to do that. Divided by 0.2, we get 28, and that's going to be in kilograms per meter cubed. So there's our density. Not too bad. For the last one, the cylinder is taken to a high altitude where the temperature is negative 50 Celsius and the pressure is that. A valve is opened and allows the gas to escape. Calculate the mass of the gas remaining. So we're figuring out how much gas is left over. So it's going to be the same thing. It's still an ideal gas. PV is equal to nRT. Now, we know that we have a different P. Our P this time is 3.6 times 10 to the 4. So what's happening is they're taking it up high and then they're opening it until the pressure equalizes with the outside. So it's going to be the same. All right, so this times the V is the same. It's the same amount of volume because the cylinder didn't change. N is what we're looking for. R is 8.31 as always. And T is going to be not negative 50 because it won't make sense with a negative number, but we have to convert that to Kelvins. Remember, it's the 273. So add them together, we're going to get 223. All right, multiply, multiply, multiply. You are going to get N is equal to 3.89 moles. But we want to know the mass of the gas here. So if we want to know the mass of the gas, we have to do the same thing we did a second ago, and we're going to multiply that 4.3 times 10 to the minus 2 divided by mole, and that's in kilograms. Put them together, and we get 0.167 kilograms of gas left. And that's how you do it. Hey, and that's your ideal gas. Should be familiar territory from good old chemistry days. All right, smash that like button and subscribe, and we'll see you tomorrow.